Okay, next topic in this last chapter that we are dealing with deals with what we call inverse functions. Now, inverse functions is pretty much as it sounds, but the mathematics of it is what we're going to teach you here, and then you'll find that this process is a fairly simple process. Again, it's a matter of mathematical manipulation, but I think that at this point in the game, you're going to be more than able to handle this fairly easily. First of all, the definition of an inverse function, and this is just the blah 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 stuff, but I want to get this to you. A function g is the inverse function of the function of f if f of g of x equals x, and I'll be showing you examples of this. And for each x in the domain of g, which means that the value of x is found in the x values of g, and the g of f of x, which is the inverse, you can see how it's being manipulated around, is going to equal x for x in the domain of f. So the function of g is denoted by f inverse. Even though it says -1, we say f inverse. Okay? Now that's not the same as f prime, so be careful of that. Reflective properties of inverse functions. The graph of f contains the point a, b, if and only if, and I'm going to be abbreviating that as IFF from now on. The graph of the inverse of f contains the point ba. So in other words, the inverse is going to have the inverted order of a and b that f had for a particular point found on a curve or line for g. The existence of an inverse function. A function has an inverse function if and only if it is a one-to-one function, meaning there can only be one point for or one value for every one value that's for your x. So you have one y for every x, one a for every b, however you want to call it. Second point. If f is strictly monotonic, it means constantly concave upward or downward. It doesn't have the curving things. It's just a continuous curve, but no inflection point. Okay? On its entire domain, then it is one-to-one and therefore has an inverse function. So all one-to-one functions, as described here, has inverse functions, and that is defined as being something monotonic. And the next one kind of addresses that. This is called the horizontal line test. You will know a function has an inverse if it passes the horizontal line test, meaning if you draw a horizontal line across the graph of a function and it intersects that in only one point, then you know that it has an inverse. The solve for x test, and this is one that I use a lot. This is one of my favorite ones. That is also well, we'll get back. Solve g of y or f inverse of x. If both give x for an answer, then they are legitimate inverses. And we're going to show examples of that. And basically, that's the same as the interchange of x and y. The resulting equation is y equals the inverse function of x. And like I said, in the practice problems that I will be doing, we'll be seeing that. This is the domain. Define the domain of the inverse of f to be the range of f. So in other words, the y values of f will become the x values of the inverse. Okay? So, let's take a look at some of the problems here. We're looking at page 347, problem number 1. And we have two functions, f of x and g of x. And we are asked to prove that these are indeed inverses of each other. So it doesn't make a difference which one you use. I go back and forth between my two favorite ones, so you can see how they're both done, but I don't care which way you use it. Just use one or both, depending on, and sometimes you can't use a particular one when you do this. But in this problem here, what you're going to do, I took the f of x and I changed that to a y. And it did the same thing here with the g of x and changed that to a y. And what we want to end up with then is the exact same formula when you interchange x and y. So I interchange x and y here. So this x came over here, this y came over here. Just change it. You don't have to do any mathematical manipulation with that. Now we're going to rewrite this equation in terms of y and see if we get the same thing over here. So I subtracted 1 here, divided by 5 here. I got y equals x minus 1 over 5, which is exactly what we have over there. They're the same, therefore they are inverses. It's that simple. The other way that we can do this, and this is a really good one, particularly if you can't do the other one very well. We have, again, two functions for number 3. F of x is x cubed, and g of x is cube root of x. So, in this case, I'm going to take the function of the g of x. Well, g of x is the cube root of x. So that becomes the function of the cube root of x. So instead of having x here, I plug that in with the cube root of x. And then I cube that, of course. Cubes and cube roots are opposites and will cancel each other out. Or in the case, if you think of it as x to the 1/3 times 3, which is x to the first, and that gives you 1x. And do the same thing over here. Take g of f of x. Well, f of x is x cubed, so we plug in x cubed for x, and we get x. When they both give you x's, they are considered inverses when you plug it in for their values for x. Number 5. Again, I went back to the other way here. I rewrote this in terms of y here. Y equals x minus 4 to the 1/2 power. And I rewrote this as y equals x squared plus 4. And then I switched the x and y around, which is why I used the red pen there. And I got rid of the square root by squaring both sides. So that's x squared equals y minus 4. Get y by itself, I add 4. So y equals x squared plus 4. That is exactly what I get over here. They're the same. Therefore, 3-dot thing, they are inverses. Number 7, and for this one was a pretty easy one to do. We're given that f of x is 1 over x and g of x is 1 over x, so f of g of x becomes f of 1 over x. And so we plug in 1 over x for x here, and they gave us 1 over x, which is the inverse, x over 1, which is just plain x. So that satisfies the conditions. We got to do the same thing over here. G of x equals 1 over x, so g of f of x, well, f of x we said is 1 over x. So g of 1 over x equals 1 over x, and that again means reciprocal. So that 1 over x becomes x over 1, which equals x. Since they both equal x, they are considered inverses. The last one is a graph problem. And I do also want to say that you can kind of see, if you do the graph of the first 4 problems, and you can see how they are inverses of each other by changing the x and y values. You can see that they are indeed inverses. Well, this kind of solidifies this. In number 9, this is the line they give us right here. And it goes to the points 0, -2, and 2, 0. Now, one of the last things that are the conditions that they gave us here in the book was saying that if you switch the x and y and then graph through that, that's going to give you your inverse. So that's what I did here. This point is 0, -2. So when you invert that, it becomes -2, 0. So -2, 0 is this point right here. This goes to the point 2, 0. Invert that, that gives you 2, 0, 2. 2, 0 gives you 0, 2. 0, 2 is right here. Draw the line through that, and then they give you 4 choices as to which of the graphs is the inverse of this particular graph. And you'll see that part, that number C, letter C, whatever, was the inverse of number 9. So you put C for your answer. But I do want you to show, when you do that problem, show the original graph, show the new graph with the inverted points that you can identify. Sometimes it's, there's one problem I saw where you really kind of needed to do 3. I don't remember if it's the one I gave you or not. So you may have to come up with 3 points because it's kind of iffy. Anytime it's iffy, do an additional point. And you get your your inverted graph. So, your practice problems. Problems 1, 2 through 12 even on page 347. Have fun.